Hello all, welcome back to my YouTube channel all about VLSI. In this particular masterclass, we are going to cover entire Verilog and we will try to understand the Verilog concepts in a very detailed manner. So stay tuned. So let us start with declaring your modules. So in Verilog, if you want to write any code, you should declare a module. So we will write a module and followed by module name. We should definitely use your module name followed by list of ports. We should mention the list of ports here. Now, in this, inside your module, you should give you the directions, direction of ports, direction of ports you should mention. Okay. And the code which you have followed by end module. Now, so this is style one of declaring your module. This is style one of declaring your module and your list of ports. Coming to style two, in style 2, we are going to write our module followed by module name followed by list of ports with directions. List of ports with directions. And followed by our code and followed by end module. So these are the two styles for declaring any module in Verilog. So first is module followed by module name, followed by list of ports and direction of ports and end module. And for second style is module followed by module name and list of ports with directions and end module. So this module name is known as identifier. This module name is known as identifier. First, let us talk about the rules when we are declaring your identifier. Rules for declaring your identifier. So basically, these identifiers are case sensitive. That means if you declare any identifier, let's say suppose half underscore adder, then you should only use this small letters, that is small half underscore adder. You cannot use HA half underscore adder with H capital in another module. Okay, you cannot call this module. So basically these are case sensitive. Okay, so this is different and this one is different because you are using a capital letter. Okay, so these are case sensitive. And identifiers can use underscores. Half underscore adder or my underscore design, like this. So identifiers, you can use your underscores, but you should not use numbers at the starting position of your identifier. Numbers are not three half underscore adder, like this. So this is not allowed. This one is not, and you should not use special characters. Special, for example, dollar my design. Okay, so this type of special characters and this type of numbers you cannot use when you are declaring your identifier. When you are declaring your identifier, so this we should be very careful when you are declaring your identifier. Now, so coming back to the syntax for declaring your module. So module followed by the syntax is module followed by module name, which is nothing but your identifier. And in the style one, we are just declaring the list of ports, and we are inside that we are declaring the direction of the ports. And in the style two, we are declaring the list of ports with the directions. Okay. So let's say if we have a design, let's say this is our design, and this design has, let's say, A, B, and C as your input ports, and X, Y, Z as your output ports for this particular design. So for this particular design, let us try to write the module. So we will simply write your module followed by design is your identifier, followed by, I'm using style one. So in style one, what we are going to do, we are just going to declare your ports. What are the ports we have? A, B, C are your ports. A comma B comma C. And what are your output ports we have? X, Y, and Z. So we will simply write X, Y, and Z as your input and output ports. And since this is a style one, what you're going to do, you are going to give the directions. If we want to mention your input ports, we are going to use a keyword which is known for input ports. For input ports, the keyword which we are going to use is in small letters input, and for output ports, the keyword which we are going to use is in small letters output. Okay, so these keywords we are going to use. So here for input ports, we are going to use a keyword which is known as input A comma B comma C, and output X comma Y comma Z, semicolon, commas and semicolon, followed by end module. So this is a style one of declaring your module. Now, in the case of style two, when we are discussing about style two of declaring your module, so simply what we will write, module design input A comma B comma C comma output X comma Y comma Z, and your code inside this followed by end module is the syntax for declaring your module. So these are the two styles when you want to declare your module. Module design, list of ports, directions, and your code, and followed by end module. And in the second style, we'll simply declaring your module. So this design is nothing but your identifier. It is known as identifier. This is known as identifier. For example, if we want to design a half adder, the simple example which we are going to see, let's say this is a module, it is a half adder. The circuit inside this particular half adder will look like this. This is an XOR gate where this is your sum, and from here you are going to get your AND gate. This is your carry. Now here you are going to connect your inputs A and B, and here you are going to get your outputs sum and carry. Now, if you want to write a Verilog code for this particular design, simply what you're going to do is you should first declare a module followed by the module name, in this particular case HA, and you can follow any style of coding. I'm going to follow style 2 of coding. Okay, so what I will write, input A comma B comma output sum comma carry, and I'm going to make it semicolon, and inside this I'm going to write my code followed by end module. So this is how I'm going to model my design using the Verilog. Now let us see the data types in Verilog. So now before going to discuss about the data types, we need to discuss about the values in Verilog. So we have four type of values in Verilog. So first one is 0, followed by 1, followed by x and z. Basically this 0 represents logical 0 or false condition. This represents logic 0, and this one represents logical 1 or true condition. And this x stands for don't care condition, and this z stands for high impedance condition. So we know 0 means logical 0 and 1 means logical 1 or true condition, and x is nothing but neither 0 nor 1. But what is this high impedance z? So to visualize this particular z, let me draw a diagram. So this z or high impedance, this basically represents the unconnected state, represents the unconnected state. For example, if we have a wire connection like this, and if this circuit is incomplete, that is this particular portion is, if it is unconnected, then this is represented by Z. So this is how we are going to represent the unconnected state in Verilog with the help of this Z symbol. Now let us talk about how to represent your numbers in Verilog. Let us try to understand how to represent your numbers in Verilog. So in digital, we have basically four type of numbers. First one is binary. For representing any number in Verilog, the standard syntax which we are going to follow is size followed by apostrophe, or you can say tick, followed by base, followed by number. So this is the syntax which we are going to follow to represent any number in Verilog. It may be binary, or it may be decimal, or it may be octal, or it may be hexadecimal. Okay. So this size stands for number of bits. This size stands for number of bits. And this base is nothing but base of a number. For example, if we have binary numbers, we will represent them with small b. And if we have a octal numbers, we will represent it with small o. And if we have a decimal numbers, we will represent them with small d. And if we have hexadecimal numbers, we will represent them with small h. And followed by our number or our value. This is how we are going to represent any number using our this particular syntax. For example, if we want to represent a binary number, let's say uh, 1 1010 base 2. We want to represent this in Verilog. So how we are going to represent? We are going to follow this particular syntax: size followed by tick followed by base followed by value. This is the syntax which we are going to follow. This, please remember, this size is nothing but the number of bits, and base is nothing but base of a number, and value is nothing but the value of a number. Okay. So what is the syntax which we are going to follow? Size is nothing but 1 2 3 4. 4 tick small b followed by value, that is 1010. So this is how we are going to represent any binary number in Verilog. 4 tick b 1010. Now if we have let's say if we have 1x0x base 2, then how we can represent this particular number in Verilog? Simple. How many bits we have? 1 2 3 4. Okay. 4 tick binary representation, 1x 0x, that's it. So this is how we represent any binary number in Verilog. Then how to represent your octal numbers in Verilog? Same syntax. Let's say if we have a octal number 435 to the base 8. Okay. Then how we are going to represent it in Verilog? Simply 8, sorry. So how many number of bits we have in this particular value? So this will be converted. If we convert this into binary, then it is 100, 011 and 101, 123, 4, 5, 6, 7, 8, 9. Okay, so it will be total 9 number of bits. So we will write 9 tick B. So we will write 9 tick O 435. So this is how we are going to represent a octal number in Verilog. Now let's say if we have 43x base 8, then also same 9 tick O 43x. This is how we are going to represent any octal number in Verilog. Now let us see how to represent your hexadecimal numbers in. Let's say if we have a hexadecimal number ff to the base 16, then how we are going to represent it? So here total number of bits, if we convert it in binary, then it will be equal to f is nothing but in binary 1 2 3 4, 1 2 3 4. So total 8 number of bits will be there. So 8 tick h f f. So this is how we are going to represent it in Verilog. So this is how we are going to represent any hexadecimal in Verilog. Now let us consider a case. Let us take case 1. Let's say if we have a binary number 32 tick B 1010. Now, what do you think the value of what do you think the value in binary? So what is going to happen here is the number of bits which we have mentioned here is 32. The size which we have mentioned here is 32 and base we have mentioned is B, and we have just simply written 4 bits 1010. So here 0101, this 4 bits will be present in the LSB, and remaining 32 minus 4 number of bits will be present in the MSB. That is all zeros will be present. 32 minus 4 number of zeros will be present. That is 28 number of zeros will be appended in the MSB and followed by 1010. So this is how it is going to append the number of zeros in the MSB if you are not mentioning all the possible values. If you are just simply writing 1010. Now let us consider another case, case 2. Let's say if we have a number represented in Verilog like this, tick B101. Now, what do you think the size of this particular number? What do you think the size, that is number of bits the compiler is going to consider? If you are not mentioned any size, this is case 2. If we do not specify the size, don't specify. So if you don't mention your size, then the compiler is going to consider the number of bits in that particular value to be 32. Same, 3 number of bits will be present in LSB like this, and remaining number of bits will be appended zeros in the MSBs. This is what it is going to happen. So this is case 2. Now, so if we don't mention the size and base value, then for example, if we are simply writing 32, that's it. We are not mentioning any, or let's say if we are writing 101, that's it. We are not mentioning the size or any base value. So if we don't mention the size, the default size will be equal to 32, which we have seen in the previous example. In the previous case only, we have seen that if you are not mentioning the size, then it will be considered as 32 bits. And if you are not mentioning the base also, then default base will be considered as decimal by the compiler. So the base will be considered as the decimal by the compiler if you are not mentioning the base. So this will be 32 bit 101 decimal value. So it is what it is going to consider. Let us try to understand the next type of data types, which is known as net. Now let us try to understand the another type of data type, which is known as net. So basically, nets are continuously driven by the combinational logic. For example, this is your OR gate and this is your output. So this is, let's say this is your input A, B, and Y. So here we are going to represent use a net, and this is also net. So what is going to happen here? So basically, the value of your output y will be continuously updating when you are going to change your input values. If you are going to change your input values continuously, your output value is also going to be updated continuously. That is, your OR gate is being driving the value continuously onto this net. So this particular concept is known as driving. If you are driving some values or if you are providing some values to the output, that particular concept is known as driving. So basically, this net, we cannot store any value into this net. We cannot store any value into this net. This is a very important point. We can only continuously drive the values into the net, but we cannot store any value into the net. So this is the meaning of the net. And another use case of this particular net is, let's say if we have two modules, this is module 1. Let's say this is module 1 and this is module 2. And if we want to connect these two modules, then we are going to use a net data type. Then here we are going to use a net data type for connecting this two modules. If you want to connect two modules, module 1 and module 2, then in this particular case we are going to use a net data type. And let's say if module 1 is sending any data, then this process is known as driving. So module 1 will continuously drive the data into the net, and module 2 will receive the data from this net. So basically this net is acting like a passage between this module 1 and module 2, and the module which is driving the data into the net will act as a driver. So the module which is driving the data into the net will act as a driver. Okay, now? Yes. Again, now these net data types are classified into different data types. So first one is wire data type, followed by war data type, and WAN data type. So let us try to understand one by one in more detail what is wire, what is war, what is WAN. For example, first of all, let us try to understand what is meant by this wire data type. Now, this wire data type is nothing but is like, this wire data type is used to make the physical connections between your modules. Okay. So using this particular wire data type, we can connect multiple components. So let's say these are your two components, C1 and C2, and if you want to connect these two components, you are going to use a wire data type. Using this wire data type, you're not going to store any value. Okay, let's say suppose the syntax for declaring your wire variable, a variable with wire data type. Let us see the syntax for declaring your variable of wire data type. You will simply use a keyword which is known as wire. Okay, this is a data type. This is a data type, and it is a keyword. This wire is a keyword, so I'm using it in small case letters, lower case letters. Okay, wire followed by any variable, let's say a. Okay, so this variable a is known, this a is known as your variable. Okay, this a is nothing but your variable, and this wire is known as your data type or keyword. So using this a cannot store any value. A cannot store any value. We can drive the values into a. Okay, let's say suppose, so we should use assign keyword when we want to drive any values into the variables of wire data type. Use assign keyword. For example, let's say if we have a wire variable wire y. Okay, so what we will do? We should use the keyword assign y is equal to a. Okay, so what is happening? This is your variable and this is your driver, or it is nothing but your source, and this is your wire A. So basically you're continuously driving the value, that is the value which is present inside this A will be driven into this wire Y. So if there is any change in the value of variable A, value in the variable A, so that will be driven into this wire Y. So this is how the things are going to be worked. And we are going to discuss it in more detail when we are discussing about this wire data type. And so let's say if we write assign y is equal to a, so this y should be always of wire data type or any net data type. This should be of only net data type only. But on the right hand side, it can be of reg or it can be of integer, anything. Okay, there is no restriction, but there is a restriction on the left hand side. Now let us see the disadvantage of using your wire data type. Let's say if we have assign, if we declare wire a and if we write assign a is equal to 0 and assign a is equal to 1. Now what is happening here? So one more thing, Verilog is a concurrent language, or it is a parallel language. Parallel execution will be taking place. That is, these two assigned blocks will run parallelly. These two assigned blocks will run parallelly, making the assignments from the right hand side to the left hand side parallelly. That is, these two statements will be running parallelly. So the value of a will be neither 0 nor 1. That is, it will be equal to a will be equal to unknown. When you have declared your variable with wire data type, and if you are driving multiple values at the same time into the same variable, if you are driving multiple values at the same time into the same variable, then you are getting your output should be, and you're driving basically don't care. Okay, so this is what it is going to happen. Now let's say if you if there is a chance of driving multiple values into the same variable of net, then we can use another data type, that is var. So if we declare any variable with var a and if we write assign a is equal to 0 and assign a is equal to 1, and in this particular case we are not going to get the value of don't care, that is in this particular case we are going to have a value of or operation. So basically this or operation will be performed on the 0 and 1, the resultant is 1, that will be driven onto this variable a. So that is finally the value 1 will be driven into the variable a. Now let's say if we have another variable, let's say vand. Now if we declare any variable with vand data type, then what is going to happen? Assign a is equal to 0 and assign a is equal to 1. Now, so the resultant, that is the AND operation, will be performed on 0 and 1, and the resultant is 0, that will be driven onto the variable a. So the resultant AND operation will be performed on these two numbers, and the resultant will be driven onto this particular variable a. So this is how we are going to use this var, vand and wire. So depending upon our requirements, we are going to use our data types. Now let us try to explore another type of data type which is known as reg. So basically this particular data types are used to store the values. Reg data types are used to store the values, and they does not yield any hardware registers, and the values are retained until the updated. Okay, so let's say if we want to declare any data type, so let's say we are going to use small keywords reg. So this is your data type and it is a keyword, so that's why it is written in lowercase, and your variable. So now you can store your values inside this particular variable which is of reg data type. You can simply write a is equal to 0 or a is equal to 1. So here you can store the values 0 and 1 into this particular variable a, which has been declared by reg. Let's try to understand this reg and net with a module example. Let's say module Please remember, there is no necessary that you should always declare your input ports and output ports. Depending upon if you are developing a test bench, then there is no need to declare your input and output ports. Okay, a module, it is not compulsory that a module should always contain your input and output ports. No, that is not mandatory. Okay, so if in this particular case we are not using any input and output ports, then what is going to happen? This will be your design with no input and output ports. That's it. Okay. So since here we are just simply writing module example, and we are declaring variables reg A and wire B. Please remember, these are your internal variables. If you have declared your internal variable, if you have declared any variables, you have just simply declared reg A and wire B. So these are basically your internal variables. So these variables will not be accessed outside your module. If you want your variables to be accessed outside the module, then you should definitely declare them with your ports, that is input port, output port, or in output. Then only they can be accessed outside the module. If you are simply declaring them with reg A, wire B, and if you are thinking that we can access them outside the module, no, you cannot access them. If you are just simply declaring them with your reg A and wire B or some any other data type, so they will become your internal variables only. They will be not accessed by outside the module. Now, if you want to use your reg variable and if you want to store any data inside your variable A of reg data type, you should either use initial block that we will discuss in our further sessions, or you should either use always block. Only these two data types will be supported. Only these two blocks will be using the on the left hand side. You can use your reg data type. Here you can use A is equal to 0, or you can use here A is equal to 1. The exact meaning of your always block and initial block we will discuss later. Okay. So inside your initial block or always block, you cannot use net data type. That is, here we have a net data type which has been declared B. So you cannot simply write B is equal to 1. No. And you cannot write assign B is equal to 1. No, you cannot write it. You cannot use your net data type inside your initial block, and you cannot use your inside your always block. You cannot write it down. Okay. You cannot use net data type inside your always block and initial block. This you should remember. Now, if you want to if you want to drive any value into your net data type, you should use assign block, simple assign block, followed by your net variable, followed by right hand side driver. Okay, in this case, 1 is a constant driver, but you cannot use reg data type with assign keyword. No. So here in this particular case, you cannot use reg, cannot be used with assign. Now let us try to understand your vectors, how your vectors should be declared, everything we will try to understand. So basically this particular vectors are nothing but a group of bits. Now in the previous examples which we have seen, when we are declaring your reg A or wire B, when we are declaring this particular variables, what is basically happening? What is the width of this particular variable A? How many bits can this particular variable A can store? This A can store only one bit of data. A can store only one bit of data, and B can only drive one bit of data. B can be driven only one bit of data. That's it. So A can only store one bit of data and B can be driven by only one bit of data. That's it. And let's say if we want to store more than one bit of data inside this A, or if we want to drive more than one bit of data inside this B, then in this particular case we are going to use our concept of vectors. Then in this particular case we are going to use our vectors. So basically what we are doing, first we should mention the data type. In this particular case I will mention it as a reg, and the size. Now here the size is very important. So you can mention the size from MSB down to LSB. So you can mention it by MSB colon LSB, or you can mention the size from LSB to MSB. There are two options. You can mention the size followed by the variable name. You can mention any variable name. Now, let us try to understand what is this MSB down to LSB and LSB to MSB. Let's say if we are storing a variable, let's say if we are storing a value 1101, if we are storing a value 1101. Now, what is MSB and what is LSB? So this is the MSB. We know. Okay, this is the MSB and this is the LSB, right? So this is MSB and this is LSB which we are storing. Now, if we mention reg 3 down to 0 a, and if we write a is equal to 4 tick binary 1101. Okay. So now what is going to happen? This 3 is the index of this particular position. So this is nothing but 3, this is 2, this is 1, and this is 0. So 0 stands for LSB and 3 stands for LSB. So the value will be stored in this particular variable a like this: 1 1 0 1. This is your variable a with indexes 3 2 1 0. Now let's say suppose if you have declared your variable with this another size declaration format, reg 0 to 3a, and your number is 1101. We already know this is MSB, this is MSB, and this is LSB. Now if we simply write a is equal to 4 tick binary 1101, then what is going to happen? What we have declared here, reg 0 to 3a. So now this will become, this will have your position index 0 and this will have your position index 3. So this will become MSB and this will become your LSB. So the value will be stored like this: 1101, while this is your LSB bit because you are having an index of 0, and this is your MSB because it is having an index of 3. So this will become your MSB and this will become your LSB. So this notation will decide what is your MSB and what is your. So let's say if we have declared a number reg 3 down to 0 a, and if we are simply storing a is equal to 4 tick binary 1101. Okay, so this will be your vector 1101. Now, so this is your MSB and this is your LSB. Now, so if you want to access your LSB bit, if you want to access only your LSB bit, then what we can write is, and if you want to store it in another variable, let's say y. So what we can write is y is equal to a of 0. So we are basically slicing our vector. We are only accessing the LSB bit and we are storing it in another variable. Let's say if we want to store LSB bit and the previous bit, that is 0 and 1, inside your another variable y, then what we are going to write, y is equal to a of 1 down to 0. That is, we are storing the LSB bit and the previous bit before the LSB inside another variable y. Okay. And let's say suppose if we want to store the first two bits, that is MSB and the next bit after the MSB, then we will write simply y is equal to a of 3 down to 2. This is the syntax for writing your, this is nothing but, this particular concept is nothing but vector slicing. Like this we can slice a vector and we can store the values which we want, the desired values. Next, let us try to understand your integer data types. So before going to understand your integer data types, let us go back to your reg data types once again. So this reg data type, we already seen that we are going to use this particular reg data type for storing the values. Okay. Let's say if we have initialized our design and we are not storing any value, then what is the default value which will be stored inside this reg data type? The default value which will be, which the reg data type is holding, is x. Okay, So the default value this particular rich data type is holding is X. And what is the size of this rich data type? By default, if you are not using a vector, then it is only 1 bit. And this rich data type is an unsigned data type. This rich data type is an unsigned data type. That is, it can only store positive values. Only store positive values. It cannot store negative values. Okay. So this was about your rich. And let's say if you are using a net data type, if you are using a net data type, then the default value which will be driven onto this net data type is Z. And the size of this net data type, if you don't use a vector, then it is only 1 bit. And it is also an unsigned. So coming to the another type of data types which is known as integers. So what are these integers? Integers are basically signed data types. Integers are basically signed data types, and the size of this particular integer is 32 bits. Signed data types are nothing but which can also store negative values. This can also store negative values. And the default value of integer is X. Don't care. So the keyword which we use for declaring any variable of integer data type is small letters integer and your variable a. So this variable a is of type integer and it can store negative values, and the size of this particular integer is 32 bits and it is a signed data type. That is, it can store negative values as well as positive values. Let us try to understand your another type of data type which is known as real. So this real data types allows you to store decimal and scientific notations, and it is not. And this particular real data type is used with the keyword small letters real. Now, the size of this particular real data type is 64 bits, and it is only unsigned. And this particular real data type default value of this particular real data type is don't care, X. Coming to another type of data types which is known as arrays. So the main difference between your arrays and vectors is in the case of vectors you are going to mention the size before the variable name. Size before the, whereas for example you are simply writing reg 2 down to 0 a. So this is a vector. Whereas in the case of arrays, you're mentioning the size after the variable name, reg a 2 down to 0. So this is an array. So for visual representation of your vector and array, let us try to visualize your vector and array. So this is your vector. So let's say if you are declaring reg 2 down to 0 a, and this is your reg a 2 down to 0. Okay, this is reg 2 down to 0 a and reg a 2 down to 0. So this is your vector, okay, with MSB bit index is 2 1 0. And whereas your array will look like this with 3 number of locations. This is third location, first location, sorry, second location and first location with location indexes 0 1 and 2. Now let's say if you want to store any value inside your array which you have declared like this, reg a of uh, reg a of 0 to 2 to 0, that is 3 locations, then what you are going to write simply a of 2 is equal to 1 tick binary 1. Then your 1 will be stored in the third location, and if you write simply a of 1 is equal to 1 tick binary 0, then your 0 will be stored in the second location, and if you write a of 0 is equal to 1, your 1 will be stored inside this particular location. So this is how you're going to store the values inside your arrays. Now let us do some coding and let us try to understand my hands on how the things are working. Now let us declare a module. So no caps, only smalls. Module example, and let's take your number at the starting position to example, followed by some input ports and some output ports and some piece of code inside your module and end module. Let us see whether will this particular module works. Let me select the simulator first in the EDA playground. So select all degree 0. Let me save this. It's getting loaded, and let me run this. So syntax error, unexpected token 2. So we'll get a syntax error if you are using a number at the starting position. That is in the identifier you cannot use a number. So we'll just simply remove it and save it and run it. Yes, everything is good. Okay, simulation has finished and there is no error. Now let's say if we have declared, uh, let me remove this all this particular ports. Let me remove this all this particular ports and let me declare a number. Okay, so let's say first of all let me declare a register. Okay, of a 4-bit. I'm using a vector, let's say a. Okay, this is an internal signal, reg 3 down to 0 a. Now let me store a 4-bit value inside this particular register. Okay, so within an initial block, what I'm going to do, initial block we'll discuss in a further sessions. What is this initial block, how it is going to work, everything we are going to discuss it. Okay, don't worry. So within this particular initial block, what I'm going to write, a is equal to 40 binary 0101 or 0110. Okay, and first of all let me display it. So for displaying I'm going to use dollar display statement. Okay, about this dollar display also we'll discuss. Okay, the value of is percentage b comma a. Okay, and I'm ending this and end module. Let me save this and let me run this. Here we can see the value of a is 0110. Okay, simply we are getting the value of a is 0110. Now let's see. Let us remove this 4 and let us try to see what we are getting. This thing we are already discussed in the theory, but in the practical also let's see what is going to happen. Let me display the value of binary this b also, and let's display it. Let's see what we are getting in the binary. So what we are getting displayed. Let me run this. So what we are getting, the value of a is 1110. The value of a is 1110 we are getting. But what we have stored 0110. Let me change the value. Let me change it to 1110. Simply I am writing a is equal to 1110. Let me run this. So I am getting 0110. So what is happening actually here? So what I have told in the theory session. So what we have discussed in the theory session, that if you are not mentioning your base and your size, it will be considered as 32-bit decimal number. Okay. Now let me open my calculator. Set it to programmer. Now in decimal number 0110. Now what is the value? Okay, we have given 1110 now. So 1110. So what is the value we are having in binary? That is 0110, 0101, 1000. Now, what is the value which we are getting displayed? 0110. The value which is getting displayed is 0110. If you see carefully, the variable a can only store 4 bits of value. But on the right hand side, you are having a 32-bit value. So you are having a so you are having a 32-bit value on the right hand side, but it is only the variable a can only store 4 bits. So that's why the last 4 bits, that is 0110. Now let's say, now let's take, instead of your reg wire, let's consider your wire. Let me save this and let me run this. So instead of reg, let's take your wire and let's see, fail. So A is not a valid left hand side of a procedural assignment. Okay, so initial block on the left hand side, you cannot use wire data types. You should only use your reg data types. So that's why we are getting our error. Now let's say, let me remove all this and simply within an initial beginning block, what I will do is I will display the value of A and let's see what is the value of A which is getting printed. I've declared a variable of wire data type which is known as A. Let me display it. So we are getting high impedance Z, so which we have discussed, right? So the value of A, the default value of A will be high impedance if it is declared with wire data type. Now let's say, let me remove this vector also, and let's say I will write assign A is equal to uh, 1, simply 1. Now let me display it. So the value of A which we are getting is now let's say now let's say if I declare the value of A to be 1 and let me display the value of A. So let me save this first and let me run this. Let's see what is the value which we are getting. So we are getting the value of A to be don't care. Let me add some delay in this particular initial block. So let me run this and let's see. So we are getting the value of A to be 1. Okay. Let's see your always block. Let's see with your always block, always begin, and let me remove this delay and let's see what is the value of A now. So let me run this without any delay in the always block. So I will explain what is meant by this always block. Here also you are getting don't care. Okay. So if anyone knows the reason why you are getting don't care, if you are not using any delay, you can comment in the comment section. Okay. I'm going to use your initial block only. Okay. With your delay, then your value will be displayed. Okay. So what is the reason why we are only getting, if we use the display, if we use the delay, then only why we are getting, you can post it if you know the answer in the comment section. Okay. Anyways, I'm going to explain it in the later sessions. Now let me change the value of A to 1 and let me display it using an initial beginning block and display statement. And let me run this. Let's see what we are getting. Okay, already we have end module here. Let me save this and let me run this. Now, so let me keep this particular delay and let's say if we are assigning A is equal to 0, then let's see what is the value we are getting. Let me run this. So the value of A which we are getting is don't care. We have seen this example in our theory also, right? So we'll get don't care. Now let's take it as war data type. Okay, and let me run this. So the value which we are getting is 1. So the OR operation between this 1 and 0 will be happening, and the resultant will be driven onto this A. Okay. Let me take it as WAND data type. Let me save this and run it. So the value will be equal to 0, since the AND operation will be performed this on this 1 and 0, and it will be stored into driven onto this particular variable A. So this is the use case. This is the usage of your wide data type. Now let's take your rich data type of 3 down to 0 A and rich Y. Okay. So I'm going to remove all this, and let's say if we are writing A is equal to 4 tick binary 011 4-bit value, and if we want to have only the last bit LSB to be stored inside our output, then what we will write, y is equal to A of 0. Then let's try to display the value of y using this display statement. Let's see what we are going to get. So the value of y which we are getting is 1. Now let's try to change the order. So 0 to 3. And let's try to display the value of y is equal to A of 0. Let me run this. So what we are getting, the value of y is nothing but equal to 0. So this concept I have explained in the previous theory part, right? So that is what it is going to happen. LSB will be this one, and LSB will be this 0, and MSB is nothing but this 1. Okay. Let me rechange it to the normal position, and let's take reg as 1 down to 0 y. And let's say if we want this two ones from the LSB and before the LSB bit, so I will write 1 down to 0. Okay, let me save this and run this. The value of y, let's see what we are getting. Now let's say of 1 down to 0. Okay, so let's see what we are getting. Let me run this. Yes, so we are getting LSB bit and the bit before the LSB. So this is how we are going to use our vectors. Now, so let me remove everything, these things, and let's say we have again 4-bit value. Let's say your value of A is equal to 3. Okay, so it is decimal 3. So the value will be equal to 110. Let me save this and run this. This we already know. Okay, A is equal to 3 means your. Okay, 1 minute. Let me change it to A. Let me save this and run this. Yes, that is nothing but 0011. Okay, since it is 4-bit variable and 3 is nothing but 011, so one more 0 will be appended and the value will be equal to 0011. Okay, let us take it as 2 only, then 2-bit. Okay, and let me display it again. It is 011. Okay, and let me display it in decimal for your convenience. Percentage D is format specifier for decimal. Let me display it 3. Now let's say if we write A is equal to minus 3. Let's say if we write A is equal to minus 3, and let me save this and let me run this. Let's see what we are getting displayed. We are getting 5. We are getting the value of 5. Here it's not Y, it's A. We are getting the value, we are storing A is equal to minus 3, but we are getting the value to be minus 5 because A is unsigned, A is unsigned, it can only store positive values. Then what about negative values? Okay. If we try to store negative values, then the negative value will be converted into 2's complement and it will be stored inside your variable reg variable A. That is what it is going to happen. Now, so let's see this particular thing in binary then. Let me save this and run this. It is 101. So basically your value of 3 is nothing but 110. I'll write it here. The value of 3 is nothing but 110. And if you apply 2's complement on this 110, it is nothing but it is not basically the value of 3 is nothing but 011, and if you perform 2's complement on this particular 011, it is nothing but 101. So this is a 2's complement that is getting displayed. Now if you want to store any negative value inside this reg, then you should use a keyword signed. Let's see if we are using the signed data type, then what is going to happen. Let me save this. And if we use the signed data type, we should allocate one more bit for the sign bit for the sign. Okay, so I'm taking it as 4 bit. Now let me display it. It is 1101. Okay, so 1 stands for negative. If the MSB is 1, then it is a negative number. So let me display it in decimal. It will be more clear. So if we are displaying, we are getting the value of A to be -3. So this is how if you want to store any negative value inside your rich data type, you should use a keyword sign or else it will be stored in a 2's complement form. Right? Now let's take your integer data type now. And okay, before that, let's remove everything. This one and this everything I will remove. And let me display simple the value of A. If you're not storing anything, let's see what is the default value which is being stored inside your A. Let me run this. So the value which we are getting is unknown. So the default value of your reg is unknown. Now, so let's say, let's take your integer A. Okay. So first let's display the default value of your integer. So it is nothing but unknown. So the default value of your integer is also unknown. Let's try to store a negative value inside your integer. A is equal to -5. Let me run this. You're getting simple A is equal to -5. That's it. So this is how your integer variable works. And let's try to store a fractional value inside your integer 5.3 and let me run this again. So the compiler, what it is doing, it is removing the fractional part and it is only storing the integer part. Okay, it is displaying only the integer part. Let's change the format specifier from %d to %f and let's see. Let me run this. Let me save this and let me run this. See. So the compiler, it is only printing 0.0000. It is not printing the fractional part. Okay. Let's take it as real. Now let me display it. We are getting 5.30. So that was about your integer, real, and net. So let's take your array now. So how you are going to declare your array? Range a of 2 down to 0. So there will be total 3 locations. Now let's say if we are going to display a of 0, that is you are storing in first location the value 1. Okay. And a of in the second location you are storing 0, and in the third location you are storing the value 1. And if you carefully observe, I'm only storing one bit of data. Why? Because here if you observe, each location can consist of only one bit because the data type is rich. So there are three number of locations and each location can consist of only one bit of data. Okay, so that's why I can only store one bit of data inside each location. Let me save this and run this. So you cannot simply display your memory like this. So the value of a, you cannot simply display your memory like this. So instead you can use your for loop for displaying all the locations. For I is equal to 0, I less than 3, I equal to I plus 1. You cannot use I plus plus in Verilog. A of I you can display. Okay. So like this you can display A of percentage D. Okay. You can display it, and you should declare your integer here, integer I. Now let me save this and run this. Sorry, you should use semicolon. So you're getting the values of A of 1, A of 0, A of 1. Sorry, here you should mention I comma E of I. Okay, let me display it now. So we're getting A of 0 as 1 and A of 1 as 0 and A of 2 is 1. So this is how we are going to print our array. Now if you want to store more than one bit of data, then you should use a vector. That is, each location now can consist of 2 bits of data. So you can simply write 2 tick binary 1 0 and 2 tick binary 0 1 and 2 tick binary 1 1. So in each location, basically you are storing 2 bits of data. Let me save this and run this. See, A of 0 is equal to 2. Basically, I'm printing it in decimal. Let me change it to binary. So A of 0 is 1 0, A of 1 is 0 1, and A of 2 is 1 1. Now let's say if you want to access the first element, first location element, let us declare a register Y. And if you want to access the first location element, you can simply write A of 0. Y is equal to A of 0. Let me remove this for loop and let me display the value of Y simply. And let me remove this everything Y. Okay. So let me try to display the value of Y. The value of Y is percentage D comma Y. Okay, or let me declare it in binary, comma y. So the value of y is simply 0. So if you are writing y is equal to a of 0, the value which is, okay, one, let me change the size to 2 bits. Okay, since it is only 1 bit, it is only showing 1 bit. Okay, let me change this to 2 bits and let me see. Yes, so the value of y is 10. Okay, so you're basically accessing the first location. Okay, now if you want to access the LSB bit of the first location, that is, if you want to access only this 0, then what is the syntax? You will write a of 0 of 0. Let us see. Let me save this and run this. So the value is simply 0. Since it is 2 bits, it is getting appended. One more bit is getting appended. Let me remove this vector and let me change it to y, and let me access this bit, the second location LSB. So what I will write, a of 1 of 0, that is second location LSB bit. Let me save this and run this. So we are getting the value of y, that is nothing but 1. So this is how we are going to access the elements from the array, and we are going to store the elements into the array. So that's all about this particular session. I hope you have got a very clear idea about the data types in Verilog. Still, we have some more data types in Verilog that we will discuss in the upcoming course. So if you like this particular video, please like, share, and subscribe to our YouTube channel. So if you like this particular video, please like, share, and subscribe to our YouTube channel all about VLSI. Thank you.